Hello everyone, welcome back. We're now in chapter 5. We're just flying through this textbook. So this time we're going over the equilibrium of a rigid body and some free body diagrams. I think we already know free body diagrams, but we've always been doing it with points. Now let's look at what happens when we actually have a body. Let me get my pointer up and go from there. Okay. So this time we're really going to focus on applications, and we will get into support reactions a little bit. So let's try this out. First off, applications. Why do we need these crazy free body diagrams? Well, it's because when we have things of size like this, where their center of gravity is matters. If I'm thinking about the forces that are applied right here by this wire, I also have a weight that acts at the center of gravity of this ramp. Then I have a moment or some other reaction forces right here at the pin connection. So there's a whole lot of information here, and the position where these forces act actually matters this time. It doesn't always matter, but it matters this time. So we have to have a free body diagram that shows that we can't put all of our forces at the center of gravity. We have to take into account where the tension applies and where the reaction forces apply to be able to solve this. So in this case, if we have something like this, how are we going to solve for this tension? Well, hopefully by this point you're always just going to default to equation of equilibrium. Equations of equilibrium, because that is the answer every single time. So we would use this free body diagram, solve our equations of equilibrium, and then we would figure out what the tension is from that. 3 equations, 1, 2, 3 unknowns. Okay, other things. Well, we might have 2 bodies here which have a force that is some sort of reaction force in between them, and reaction forces with what's holding them in place. If we want to determine all the reactive forces, we can't just say, well, we're going to look at this body by itself or just this body by itself. We have to take into account all of the bodies if we're going to do that. So that is important. So once again, we have to figure out a lot of information here. But if we look at this, we have 1, 2, 3 unknowns. We have 3 equilibrium equations. We can solve this. It's just we have to take into account some distances. We have to make those ourselves. So don't get freaked out. You've already more or less done this. It's just kind of defining it in a little bit more detail now. Okay, so first off, what does rigid body equilibrium mean? Now, when we have a particle, all those forces act at the same point. It means they're concurrent. They hit at the same point. However, with a rigid body, they're not usually concurrent, and they may cause rotation of the body because of the moments. So we have to make it a little bit strange. We go from a point, it's gaining some weight, it's now a rigid body. So for a rigid body to be in equilibrium, the net force, which we've seen before, and the net moment at any arbitrary point we choose must be equal to 0. I'd be like, well, why any arbitrary point? Well, question for you. If your table, just is sitting there, it's at equilibrium, fine. Do you ever see like a part of your table just pop off, just out of nowhere? Just kind of jiggle and wiggle around, pops off, comes back. Doesn't happen. If your table's in equilibrium, then every single part of your table is also in equilibrium. That's what we're getting at right here. Okay, so how do we solve these rigid body equilibrium problems? Well, first we need to create an idealized model, which is this right here, because obviously we're taking out the fact that there's some imperfections here. Maybe these 2 chords aren't exactly the same length or exactly the same angle, but we're doing our best. There's going to be some error, but we're going to try our best. Okay, so we've set it up. We've got it as close as we can. And then we need to create a free body diagram. Now this free body diagram shows all of the external, active and reactive forces acting on our body. Rigid body in this case would be the ramp, and then these are all the forces. So we replace any ropes or pins holding it in place with reaction forces. We also make sure that we take into account the weight, if it's necessary, of our rigid body. Then we will apply the equations of equilibrium to solve for any unknowns. Okay, let me see, make sure I'm not going. Yeah, I'll stop here. And next time we'll go into more about free body diagrams and the reaction forces. But just remember, this is not anything all that crazy. You've more or less done this before. It's just in previous cases we were typically giving you the forces. And now we're saying, okay, here's some ropes. What are those ropes going to do? They're going to be a force. What's that pin going to do? It's going to be a force. So we're just taking you one step further, one step at a time. So I hope this helps you, and I'll see you all next time as we talk about these free body diagrams and how we take into account these support reactions, like this wire right here, or this pin connection right here, and how we denote those on a free body diagram. See you next time. Bye-bye.